Welcome to the Digital Forester podcast, where we talk to foresters about how they are using digital technologies in their day-to-day forestry work. Hey, everybody. Welcome to the Digital Forester podcast. Today, I'm joined by Dr. Dale Freed. He's the founder and CEO of 3DEO. Dale, how are you today?
Hey, doing great. Doing great. Thanks for having me on.
Good stuff. Good stuff. So where are we reaching you today in this world of digital? We never know where people are, but I believe you're somewhere in the US.
Yes, that's right. I'm in the roaring metropolis of Norwood, Massachusetts, which is a suburb of the Boston area.
Okay.
Been here for a while.
Very cool. So I know looking just for the people, our audience and our viewership, we are going to be talking about lidar, a different type of lidar today, but Dale is also going to be showing some data. So typically, we've got the audio podcast just for those who often are on the audio side. This is one at some point you might want to switch to the video, the YouTube side, if you want to check out some of the visuals, since obviously we can describe it to the best of our ability, but at some point, counting millions of photons and trying to explain that verbally is just, at least I will epically fail in that description. So I just encourage some folks, you may want to go on the video version of this podcast later on in the day. So just to kick things off, Dale, I know looking at LinkedIn, you're a physics guy, bachelor's degree in physics from Washington State University, and then PhD at MIT. So maybe walk me through your, to get started, like how did you just always love physics? You're always a technical person, but what drew you into that space to start off?
Yeah, no, thanks for the question. I started in electrical engineering, actually. My dad was an electrical engineer, and I knew I enjoyed technical things. But I kept getting told that quantum mechanics was just weird and magic somehow. And I'm like, that can't be. And so I took a few more physics classes and I found I really enjoyed it. And then I did some undergrad research with a professor in the chemistry department, physical chemistry. And that made it pretty obvious. I wanted to go more on the sciencey side than the engineering side. Although now it's interesting. I'm back to doing engineering and I really enjoy it.
Yeah, very cool. I know it's funny. I have a good friend. He's in the quantum physics world of things. And when I remember one time we were camping and we were talking, and he said about forestry and remote sensing. He said, it's so interesting. And meanwhile, he's living in the qubits world and all stuff I don't understand. But I was like, I think your stuff is like way more interesting. He said, but no, you get to go out, in the field, touch things. It's like I'm in this theoretical world working with these models, and I'm like, oh, okay, I guess to each their own perspective there. But maybe for our listener, I'm curious. As a Canadian, you're an American. Was it easy to get into MIT? Was just you just had to score really high on the courses. It was just a walk in the
Trivial.
park. But tell me maybe that journey, because that was coast to coast, right? As a
It
young kid.
was. Yeah, no, it was. Well, the folks at MIT took a real gamble on me, I would say. They probably wanted someone from out west or something, but no, the professor that I worked for as an undergrad, I think he wrote a recommendation that I really appreciated. I never read it, but I assume that's what helped turn the tide. But yeah, no, it was quite a move. I remember Washington State is out west; it's dry. And August, I showed up in Boston and I walked down the jetway coming off the jet, and I'm just like hit with this wave of humidity. And I said, "Oh no, what have I done?" But yeah, I ended up staying in the Boston area, and it's
I
good.
was going to say you're still there, so obviously something, some aspect, you found a liking to. So very
Yep.
cool. So for our listeners and viewers, right, this is a forestry technology podcast. We will get there. For many who are listening, I'm going to be asking a lot of dumb questions on my behalf and maybe our listener and viewers' behalf, since we're going to go into a space that's quite different. So Dale, historically in our world, it was airborne laser scanning or lidar, and then now over the last couple of years, we had linear lidar, and I think back to the days in forestry where we were just talking about scanning a transect of lidar. Ross Nelson from NASA Goddard Space Institute, very early technology. But now there's this language of linear mode, there's single photon lidar, there's Geiger mode. So I'm going to take us back and, as I said, ask some of the basic questions, and some of our viewers, either one, they've heard of single photon lidar, they've heard of Geiger mode lidar, or I'm suspecting some foresters, boots on the ground, Jane Forster are going to say, I'm not really an expert in lidar. So I'm wondering, could you maybe, to start us off, give us some basics in terms of the differences of Geiger mode and linear mode, what we're used to, and maybe to kick things off, like Geiger, is this like what's the meaning of Geiger?
Yeah, no, certainly, and this is a subject I'm very passionate about. You might have to stop me at some point, but you've heard of Geiger counters, where you have an X-ray or something that comes through a tube, and then it goes click every time you get a incidence of radiation. So what we're talking about here is a kind of a solid state version of that, where we have a photodiode, very much like you would use in a linear mode lidar, where it absorbs a photon and it creates an electrical signal. But the difference is these particular devices, and we're talking about individual pixels that are maybe 50 microns, so 0.05 millimeters in size. Each one of those is optimized to act as a Geiger counter. So in particular, when you get a photon that hits it, instead of having a very tiny electrical signal that you have to amplify up with RF amplifiers and that sort of thing, instead, the way these devices are made is there's actually a volt level voltage fluctuation. And so that's much easier to detect. And in particular, there's been a huge amount of development done by multiple organizations, including MIT Lincoln Lab, where I'm from. So I'm kind of biased, as well as other places. And now they're commercialized, so you can buy these devices, where there's whole arrays of these, and behind each pixel, each of these little Geiger counter pixels, there's a digital circuit that's a timing circuit. So in particular, you start the clock when your laser pulse goes out, and then the clock runs at a kind of a 2 gigahertz rate. So it's counting really fast. And then when that photon comes in and there's a click, then we stop the counter, and that gives us the time. So we have really a stopwatch. And sometimes people say it's a photon to digital converter, or a photon to time converter, where a photon comes in and what comes out is a digital number that represents time. Often in cameras, we think of the digital readout being the brightness, or a brightness in a color channel. Here, the digital readout is the time of arrival of an individual photon.
Okay, very, very cool. And is this, I know you mentioned with the Geiger side of things, it doesn't sound like that aspect is bleeding edge. Maybe that's been around. Is it a fair statement to say it's more how these technologies have come together that creates the innovation? If that's true, what's the origin of Geiger mode lidar? I believe, doing my research, there's some DARPA or some defense connotations, and as we know, the internet came from some DARPA R&D and stuff. But how did this come about, or maybe what was the driver behind this Geiger mode technology? Because again, in the linear mode world that a lot of us end users are familiar with, this is kind of a new space. Things, at times when I've thought about it, I'm like, is this the radar equivalent of remote sensing, where it's just a bit more complicated and scary enough, versus we've got satellites taking multispectral or hyperspectral imagery, but it's a picture I can relate to, versus radar technology is just a little bit different. But with this stuff, like, where's the origin for this, or the trigger to say, hey, maybe we could use this Geiger mode stuff in a lidar world?
Yeah. So to the best of my knowledge, there was a desire in the defense and security world to be able to do lidar kind of sensing, distance sensing with a laser, at very long distances, looking at missiles or things like that. And in order to be anywhere close to eye safe at reasonable distances, there was a real need to reduce the amount of power that was required. And people looked at technologies that were available and found that if you work through all the math for, at the end of the day, what does it take to be able to do a range measurement with these, and I'll call it a photon sensitive system where we're sensitive to individual photons and we're recording each one. Those kinds of systems allow these range measurements to be done with high confidence with on the order of 5 detected photons. Whereas in a more a linear mode system, the noise sources and stuff are different, and the physics is a little different for the detection problem. And to get a similar level of certainty, of reliability of doing your range measurement, it turns out you need hundreds and often thousands of detected photons to get a reliable result. And so for looking for long distances, or for low size, weight, and power, if you don't want to have a big laser, you want a small aperture, a small laser, then working in this photon counting regime or photon sensitive regime, it turns out to be better. So in the defense industry, there was a lot of development, in particular taking Geiger mode avalanche photodiodes, these detectors, and turning them into arrays. So make a whole camera out of these things. And so that now you're doing thousands, tens of thousands of measurements in parallel at a very high rate. So it started in the defense industry, the best of my knowledge. And then in the last, 7 to 8, 9 years roughly is where there's been some tech spin-outs from some of the government labs to produce these camera devices. So you can go buy them now and design them into products, and they can be built and developed.
Cool. So I feel like we need a episode of Jack Ryan or something on Amazon Prime to show Geiger mode stripping away the trees and seeing the tanks or missiles hidden under the foliage to draw that parallel. But you mentioned you're coming from MIT Lincoln Lab. Is that the genesis of 3DEO? Because 3DEO has been, I think, based on the LinkedIn profile, around for 8 years. You've been leading that, but was that the spark, I guess, with MIT Lincoln Lab that got you interested in this and propelled you into 3DEO?
It really is. Yeah, when I started at Lincoln Lab, I had never heard of a lidar before. And I had a great boss there who got me into this area, and I was able to devote the vast majority of my professional life at Lincoln Lab to Geiger mode lidar system development and demonstration. So it was a great amount of fun. Yeah. And kind of got to the end of a project, and seemed like the stars had aligned both from a market standpoint and a component availability standpoint. And in my personal life, it was a great time to go out and commercialize it. MIT Lincoln Lab does a great job of doing system demonstrations, technology development, but their mission is to do kind of that core tech development and then transition it to industry to start, commercializing, to build it, build many copies of things. And so, yeah, it's been a great run.
Cool. So I know you mentioned that there's an eye safety component. So often, in the linear mode, right, we've got to be at a certain altitude because it's using like a class 4 laser, and from a safety is paramount. But I'm in the world I'm used to, I guess these lasers are in the infrared or near infrared ranges. What can you tell me about the physics, I guess, or the wavelengths of the lasers? Are they the same wavelength, or are they somehow different?
There's different options available. Some of the first Geiger mode APD arrays, the cameras, were made with silicon, and it turns out that the physics is such that you want to use visible or near visible light. So 532 or 780 nanometers. There's also Geiger mode APDs that work at 1 micron, which is what our systems tend to use, and that just has to do with the availability of laser sources and detectors. And then there's also ones at 1.5 micron, and there's work that goes up beyond that as well.
Okay, very cool, very cool. So in my research prepping for this, and again, I've heard, I think the first time I heard about Geiger mode lidar might have been going 5 years back, and at the time, there were some challenges in terms of the data processing. Again, as you know, 5 years is, you know, eons in the compute world. Like, you know, the amount of data we can move, the new technologies has changed. But I'm thinking for our listeners and audiences, Geiger is different in the sense of how it scans and how it, you know, it's not, let's say, doing a linear mode sawtooth pattern, beam pattern. You're actually, I believe you called it a field of regard, where you're actually looking at it from multiple angles. So as the aircraft's moving through, you're kind of, I don't want to say shooting at it, but kind of shooting at it different perspectives. Is that a fair description? Or maybe could you describe to us how we go about acquiring data in Geiger mode? Because again, I believe, as you've alluded, you're counting individual photons, and I'm assuming that's being counted at a voxel level, so a three-dimensional pixel, and depending if there's a threshold, you're saying if there's something there or not. But just by saying that, I'm also like, wow, this is like next level Star Trek-y compute, because like how do you, like, there's got to be billions of photons you've counted, right? So
Right.
maybe to start things off, how do we acquire LiDAR data? It's an aircraft, a drone, or it's kind of usual missions, and we'll go from there.
Yeah. Lots of you gave me a wonderful platter of things to talk about. Geiger mode has to do with the technology of the receiver itself. Now, you can make a LiDAR, you can put the pieces together in different ways, optimizing for different things. So the photon sensitivity part means that you can take a lot of measurements very quickly and from long standoff at low power levels. For example, in our systems, you know, a typical data recording rate might be on the order of 200 to 500 megabytes a second. And the vast majority of that is 2 bytes per detected photon. So you can, I guess that means on the order of 100 million detected photons per second. Now, we typically plan our collections so that for each, you know, what I like to call a resolution element on the ground, and a volume in which we would like to see if there's something there or not. Maybe it's a square foot, maybe it's 10 centimeters. For each one of those, if I really intend to get a reliable measurement, I plan for on the average of 10 detected photons, because sometimes things are brighter or dimmer or whatever. So typically mission planning, we plan for on the order of 10, maybe 20, depending on what we're trying to do. So now with that 200 million or 200 megabytes a second, you know, 100 million to 150 million photons per second. Now I maybe divide that by 10 again. So now I'm down to 10 to 15 million kind of finished measurements per second that we do. And if, I'm kind of making some generalizations. So that's the detector side. Now you ask about the scanning, and we're really proud of that. We've implemented scanning in a little different way than some other folks do. And we think it has, well, we know based on our experience, it has a lot of utility, in particular for urban mapping as well as for forestry. So the idea is, because we're using a camera, I like to think of it as like my cell phone camera, wherever my cell phone is. I got my camera, and I have a flashlight, right? And the camera is small. It's kilopixels. It's like 4 kilopixels. And so it's quite small. And so I make my flashlight, my laser, small as well. And now I can scan those two things and point them wherever I want. Now, the fact that the camera is not just a single pixel, but it's actually kind of large, means I don't have to move it super, super fast. In some linear mode systems, if I just have a single laser beam, I have to really zip it around really fast in order to use it efficiently. So here I can move a little slower, which gives me some more flexibility in terms of the technology that's available for the scanners. And in fact, we've put together a scanning system, and I work with a great team of people. They do all the hard work. We have these 2 mirrors that are orthogonal. They move the beam in orthogonal directions, and we can address a total area looking down from the airplane Or we also have a sideways looking system for a different project, not forestry. But looking down from the airplane, we can do plus or minus 20 degrees. So 40 degrees total in the along track direction and 40 degrees total in the across track direction. So that means as we fly along, a given point on the ground, we can look at it looking forward, and as we fly along, we can continue to look at it as we pass by it. And in fact, and I'll stop here in a second. You've been nodding your head very, very interestingly. Thank you. What we actually do is we divide up the ground into a set of polygons, a whole trail of these polygons. And as we fly along, we kind of hop between those polygons, and we interrogate each one once, and then we interrogate it again, and then we do it again, and we do it again. And at the end of the day, as we've flown over, each one of those regions on the ground gets looked at from multiple angles. And that's important for forestry, obviously, because you want to find some holes to look through. And so by looking from many angles, you can kind of fill in the ground better, or fill in the tree trunks or whatever. In an urban mapping situation, that's also important because you want to get the sidewalls of buildings and look under the awnings and all that sort of thing.
Yeah, for sure. No, definitely very cool. And I'm nodding here for those who are watching, because I'm stitching things together, and like so many questions are popping out, because one, it's kind of sounding like how you're scanning is unique to 3D EO versus the Geiger's. Maybe some of the
Right.
parts are general, so that's unique. So for the lay guy here, often I like to paraphrase things into things I can understand. But if I heard you correctly, like you got an aircraft moving, and basically, like your smartphone analogy, I'm kind of flashing, looking at the ground like multiple times based on how your scanning technology works, which is neat. And so maybe tell me about how high you fly and what that means for coverage, because I'm assuming by connect the dots, this means you can fly higher than traditional linear and go faster than a traditional linear mode, which means cheaper, more data, better data, and cheaper. Maybe, is that a fair statement?
That's what we're trying to do. We are actually seeking to understand better what the exact requirements are for answering different questions in the forestry industry. If you're just looking at the tops of the trees, then we don't need to kind of pound as much light down at the ground. And so flying higher, scanning wider, is very appropriate. If you have dense foliage and you're really trying to see the ground or the tree trunks in high degree of detail, then you have to slow down. But frankly, all systems have to slow down to do that and to poke harder. So back to your question, yes, flying higher, scanning wider is part of the competitive advantage we have. But I think also, in addition to that, with the Geiger mode systems, because we're detecting and time stamping photons one at a time, it turns out we can aggregate together many, many, many laser pulses, thousands of laser pulses, even the ones taking from different angles looking in. And at the end of the day, we put all of that raw data together, and then we look to see, did we get our 5 to 10 photons from a surface under the canopy? So in other words, the amount of light that we get back on any laser pulse can be exceedingly small. 1% of a photon on average, meaning it would take 100 pulses to see even one. Whereas with a linear mode lidar, one of the differences, there's typically thresholding circuitry, analog circuitry, and there's noise going along here, and it's looking for a pulse, right? But if that pulse is down in the noise, you just can't pull it out. And so that's one use case where, in a highly obscured environment, using this Geiger mode technology can be quite beneficial.
Yeah, yeah. They're definitely very, very interesting. And so thinking of that flight altitude, is it 10,000 feet, this thing? Because it sounds like, if I'm hearing you right, I hate to say, but it's like, well, it depends, Kevin, what the use case is and what we're trying to do that will determine the flight. But it's sounding like it's not like a linear mode, like, and again, some of the linear mode can go higher, of course, depending on the point density target. But it's sounding like this is what, like, is it a 10,000 foot type of flight, and how much area can we cover given an average point density? Like what can you give us as number
Yeah.
one so someone can relate to it in their head?
Yeah, a good rough number for looking at just the first surfaces of what's out there, just urban mapping, say, for example. Flying at 10,000 feet, we get area collection rates of around 1,000 square kilometers per hour at point densities on the order of, and I'm sorry, I don't want to lie to your viewers, and I'm going to just cheat here for a second. Um, 25 points per square meter,
Wow. Okay.
something like
Okay.
that.
Yeah, very cool. Yeah, I remember early days where we were half a pulse per square meter, 1 point per square meter or a pulse per square meter. So this is very different. But that's a good comment because it's going to lead me down a different question, which I suspect it's not a straight answer. In the linear mode, often it's like, all right, it's like we're targeting, I want 5 points per square meter. I need 16, I need 50% side lap, etc. I'm sensing because we're counting photons for any flight mission, it's not as cut and dry as here's the point density, because it sounds like the point density is variable to what you set maybe in your data processing because you're counting the photons per voxel. Is that a fair statement? And if true, the follow-on question, a two-part, I guess, is talk to me about point density in this Geiger mode, but as well the voxel. Like, are these like big voxels? Are they kind of small, or how does that world look like?
Yeah, no, that's a great question. And it is different. So I'll back up just a second to say, uh, in the Geiger mode systems where we have a detector array, actually this is true for all flash lidar systems where you're using an array of some sort. You get your spatial resolution on the receiver side. It really is an imaging system that's illuminated by a laser. Whereas with a lot of linear mode systems, in fact, I think the vast majority, there's one or maybe two laser beams, and the narrowness of that laser beam sets the spatial resolution. Okay, so that's important to say because now on every laser pulse, I get returns from all these different pixels. And especially with Geiger mode or single photon, I have to, in processing, go, try to find, where do I find these lumps or concentrations of photons? Most likely that's a real surface. There is noise that does come through. Sometimes, things happen. Either there's a little bit of background light or something, but those are photons that are not correlated with any surface. And so we have to go exclude those and retain just the ones that came from a surface. So as you said, as you indicated, the resolution at which we do that can be adjusted in processing. We don't have to use the spatial resolution of our imaging system. We can be coarser if we want. So for example, sometimes, I might fly, for example, at 10,000 feet, my spatial resolution on the ground, that is to say the size of my pixels with the appropriate amount of fuzz around them, that's on the order of 24 centimeters. But I might make a data product that is half meter resolution because I just want a lot of area quickly and I can tolerate less resolution. So that saves the customer money. They don't have to, they can fly, they can scan wider areas. And with our agile scanning system, we can program in on the ground, is that a 500-meter swath, a 1 kilometer swath, or whatever. And regardless of the altitude of the ground, the roll and pitch of the airplane, we always scan just the area that we were intending to scan. That's a lot of words. I hope that helps.
Yeah, no, it's really cool. That's why I joked it's lidar, and yet it's not lidar because it's different enough. Because just as you described that, the number of photons that you're counting, like this is large volume data. So thinking of a typical job, or what would a typical job be? Is this like, thanks, I've flown the 3DO Geiger mode. I'll talk to you 5 years later because the pipeline, the data processing pipeline will be done then because there's so many points. I'm assuming there's some magic behind the scenes to pump this stuff out quickly, especially if you're maybe a 10-centimeter voxel and counting and saying, I've detected this. Is there a threshold that's exceeded? And yes, that's a real target. But I'm assuming that's a lot of data. Like, what's the typical turnaround for a project?
Yeah, no, that's a great question because the on a linear mode lidar where there's an analog detection circuitry, you're doing kind of analog computation, right? And you get the answer pretty much immediately. So here we're doing all this digital signal processing, which is great because we can dream up all kinds of fancy algorithms, but it's a downside because it takes time to run. The short answer to your question is right now at 3DEO, our processing pipeline is not nearly as fast as we would like it to be. We've spent a lot of time building the hardware, and we've started using that hardware for customers, and we're getting the processing in shape. However, the good news story is, as you might imagine in the DoD world, no general is going to wait for a year to get his product, right?
Right.
And so, in fact, there are multiple programs where there's effectively real-time onboard processing of this data with a reasonable kind of swap of the size, weight, and power of the processing system. So we know it's possible. We're working on that and very excited about some of the directions we're taking on that.
For sure, very cool. And so I guess from that comment, Dale, just for clarity for our listeners and viewers, so 3D, you're manufacturing these Geiger mode systems and selling them the hardware and the processing.
Right.
Less, you're not renting them, or you're not necessarily a acquisition company. You're a manufacturer of the technology. Is that
Yeah,
is
we'll rent them to you if you want to rent them. And we also are doing some collections for people because really the technology is different enough that I wouldn't expect anybody to just jump in with both feet and they want to see some test data.
yeah.
How does this really work, and do you really get the performance that you're talking about? And so we're really happy to do some of those kind of proof of concept demos, and we've done several of those so far.
Sure, very cool. And I believe you have a Zion 1 sensor, a Zion 2, and then so it seems like you're progressing the technology on an order of magnitude, like from a cost, because again, foresters, they're probably waiting. They know they're secret, like, when's he gonna ask? When's he gonna ask? Foresters normally always ask within the first 30 seconds, how much does this cost? Because if it's not realistic, like, we don't even need to talk anymore. But not to put you on the spot, but from an order of magnitude point of view, I know linear lidars can often be million and a half range. Where does your technology sit from an order of magnitude point of view?
Well, we would charge as much as the market will bear. But the fact of the matter is, um, uh, our value proposition is a sensor that's on the same order of magnitude of cost as the very best systems you could buy from somebody else, but with substantially increased capability. We have to make it compelling for people to want to try our stuff out.
Absolutely.
And so we figure if about the same cost, maybe a little bit more by the time you get all the processing and everything put together, but not 2x,
Right.
definitely less than 2x more,
Yeah,
but a lot more capability, which
sure.
really helps in a lot of situations.
For sure. So before we switch gears more into the forestry side, because I think this is the good Geiger mode 101 and the 3DO technology 101, hopefully for our listeners and viewers, you're like, okay, I generally get how this technology works. But when we draw the parallel into the forestry world, it's super cool because one, it's like, and I'll get you to talk about it in more detail, but you can strip the canopy off a stand, a forest
Right.
stand. You could potentially, in some of the data sets, and I'm just paraphrasing because Dale was kind to share with me a presentation before this, which we'll talk about at the end, or maybe I'll get you to comment it on in the end. But we can see the shadows of the trees in your data set because as you're passing by, as you said, you're kind of spotlighting from different angles, which kind of blew my mind away, to be honest with you. You kind of see like the shadow of the tree. It's like, that's not a photo, right? Like multispectrally, optical, like this is an active lidar, a laser, but yet I'm seeing the shadow of this tree trunk on the ground, which then my understanding is you're stitching all these scans together to count in these voxels to see if I've got something there. And I'm sure I'm bastardizing the magic of science there. But let's go into the use case of forestry because some people are probably dying to know like what does this mean for me? But those are two examples that struck me as very odd. And you commented earlier is, well, I can see from different angles. And so when we think about forestry with pretty dense canopies, this is a compelling point because you might not see it the first shot, but if I'm looking at it from multiple angles, maybe I am going to get more penetration, maybe even see the tree trunks themselves. So maybe what's the genesis of 3DO and forestry? How did this come to be where you're like, you know what, I'm going to scan some forests? And I'm sure the forester is like, Dale, I got no money. It's like, are you right? It's like, can you pay me any? No, no, it's like, I need to do a trial. I need to do a beta, right? Before I do something. But what was that spark for you to get into the forestry space and say, hey, what can we do with this technology?
Yeah, good question. And so actually within the DoD, one of the unique capabilities of lidar is being able to look under the canopy. A lot of 3D measurement of cities or something like that, you actually can do, as I'm sure you're aware, with cameras that are, you do the photogrammetry, putting together the imagery from many angles and do the trig and turn the crank. And I'm sure it's a very complicated crank, but out comes 3D imagery. You can't really look through foliage if there's any amount of occlusion at all, except with lidar. So in the defense and security world, lidar has a really unique place and a compelling value proposition there. So we've done a lot of work looking through dense canopy, both on systems that we've built and systems that we've helped build, and previous lives, systems that we've built and systems that we support and all that sort of thing. So it's very natural for us to think about forestry. We're usually trying to find stuff on the ground. And so the idea of looking at the stems of the trees, that was kind of interesting. And, a partner that we've worked with for quite a while on other projects came to us with a forestry particular application, which got us thinking about the forestry, the metrics for the trees themselves. And I'm gonna need to stop right there because I'm kind of getting close to the edges of some NDA, so I'll just stop with that.
Absolutely, for sure. Yeah. So definitely, again, for our viewers, listeners, I always brief our people on the show. It's like, share what you can openly, but at some point there's always going to be some sensitivities. So that's totally fine with that. So thinking of that, would you say the adoption of foresters, and again, I tease my forestry colleagues, like, I'm not saying you're all cheap and never do any R&D innovation, and I'm sure there's people busting out laughing because they know what I mean, but I'm not saying that, but I'm going to tease my community there because in some respects foresters will go full tilt on a piece of technology, don't even care about cost as long as it solves the problem, is easy to use, and it works. So with this, what would you say the adoption rate of Geiger-mode technology, or I will say Geiger-mode technology in general, not just 3DO technology, would you say it's like 50%, 25%, 100% maybe, or like 2% or zero? Like where are we in that spectrum?
Yeah, well, I'm not obviously privy to what my competitors are doing. My sense, though, is it's really at the infancy. And I think the reason for that is a lot of the analytics that you have to calculate, things that are actually, like you said, solving a real problem. Like this, I've got, 300 acres of timber here. What's it worth? Right? There's a lot of math to do between our output data products and that answer. And I think the people who invest in that will reap huge benefits because we'll be able to provide that input data over large scales at a very affordable price point for high levels of detail. We're talking hundreds of points per square meter effectively. I mean, they're kind of distributed down vertically, but these high point densities, measurement densities, maybe I should say.
Yeah.
So I think there'll be a big upside for people who are willing to make the investment.
So I guess thinking before we go into the visual, because I know we set them up right at the start, Dale. We're like, we're going to show something. So they're all switch to the YouTube video side waiting, going like, they're just talking. Why? I'm in the car, like I stopped and I switched. But before we go there, a question, another dumb question. Again, I know I'm very good at asking these dumb questions. Single photon lidar, Geiger mode, are they the same? Just called different things, or they're different?
I don't want to speak for my colleagues in the single photon world. My interpretation is it's basically the same. However, they've at the Sigma Space, which is now part of Leica Geosystems, they made some slightly different system trade-off choices in the signal levels that they use and the amount of background noise that they have. And yeah, I'll leave it there because I don't want to say anything negative about their technology if I don't understand it.
Right.
It
Right.
certainly is. It's photon sensitive. They're digitizing the time of arrival of individual photons. There's certain technical advantages that their detectors have as compared to our detectors, and there's disadvantages as well.
For sure. So the commonality is you're working at the photon level, not a pulse, laser pulse level.
Right.
Yeah. Okay. So
Right.
it totally makes sense. So maybe do you want to share your screen? I know
Sure.
not we, who am I kidding? It's not me. It's like Dale did all the work, but Dale's prepped a visual to kind of what's the right saying, to maybe put color to the, I'm terrible with these things, but to really show what this data looks like. So we're going visual now. So again, for the people who are listening to the audio podcast, I'm just checking, we'll probably, at the 40-minute mark for those maybe who are watching this after. But I'll turn it over you to Dale to maybe just comment. We're looking at a point cloud, obviously a freaking super dense point cloud, but I'll let you take it away and describe what we're seeing.
Yeah. So this is a little small segment of a much larger point cloud that we collected, and I'll just say that we collected this at a area collection rate of about almost 30 points per 30 square kilometers per hour, just to kind of set the scale. Whenever you make statements about lidar productivity, you always have to talk about point density, which I'm showing you, and area collection rate. So this is a top-down view, and I've cut the side so that we can turn this and look in from the side. And so right now we're just looking down at the tops of the trees, and the color is the Z coordinate. And I'm going to change the coloring to be going across the image. And I think you'll see here in a second why I'm doing that. My 8-year-old Mac is a little bit slow here, but if we rotate this around, you see these trees here. And again, this is data that was collected at about 30 square kilometers per hour. And I'm going to, click on one of these trees here and just kind of zoom into what we're seeing. I'll make my points just a little bit bigger. And to me, it's really exciting to see the level of detail on these deciduous trees. These are mostly deciduous trees. This is a mid-Atlantic scene. But look at the level of detail on these tree trunks, on the branches. You can see where the trunk splits, the stem splits into multiple pieces. And you're also getting excellent coverage on the ground. Now, there is a caveat. This was collected in late March, mid-Atlantic. It's partial leaf on. So it's a great data set, except that the foliage wasn't completely out yet. So I just want to set expectations there. But this was, I believe, about 12 different view angles that we collected over the course of 4 different flight lines, looking at each point on the ground. Because it is the Geiger mode data, and we have all these photons, we like to play games with how we look at it. And you mentioned the different algorithms that one can use to process it. This I'm going to change a parameter here, which has to do with the confidence of the measurement. So I can turn that parameter to a small number, meaning I'm going to show all points, even if they have a low confidence. So that means there's also going to be more noise. So let me do that. And of course, now you see, yep, there is. I'll make the points a little smaller. There is a lot of noise under the ground. There's a lot of noise through this cloud, but you also see the outlines of these trees. So you kind of feel like, yeah, we ought to be able to do something with that. On the other hand, if I set this threshold much higher, so I'm saying, yeah, I only want to look at points that really have a high confidence, I see that as well. And this is the kind of capability or a quality of the data that I think will be very useful to people doing machine learning analysis of this kind of data. It gives them some extra knobs to turn so that they can kind of turn it down and look for fine details at the expense of more noise, or they can turn it up to get those big, solid, gross features. So I'm looking forward to sharing this kind of data with anybody and everybody who wants to play with it. We have data sets available to share.
Yeah, so
I'll
very,
stop
very,
there. Yeah.
yeah, very cool, Dale. Like, so for those who may be listening and not watching, and you can do that later on, just to describe maybe again in the Kevin Lim layman's view, I'm seeing, branch structure. I'm seeing the tree trunks. So for us who are used to airborne linear mode lidar, we're used to seeing points in the upper canopy and then maybe one or two, points on the actual stem of the tree. In this case, I don't want to say it looks like a terrestrial laser scanning data set, but to some extent, like I can see every single stick there and even some understory structure. So again, I think this is the interesting part, Dale, where you're saying because your technology scanning and looking at the same geolocation, I think is the word you were using, from multiple looks, that you're kind of almost, if I can't see it this way, then I might be able to see it from another look, and stitching that together, which then gives you this really rich data set of all these points. And again, when Dale switched it to the confidence level, this thing blew up to like, tons of points, a lot of noise. But again, that makes sense because you have filled this 3D space with, or recorded, I should say, this 3D space with many voxels, with many measurements. And you're just kind of thresholding, I guess, each of those voxels to figure out, do I have something there? And I'm sure there's advanced capabilities there, but super cool. So for those who are listening, it's worthwhile when you get back to the office to jump on the YouTube side to take a look at this video. So thinking, I'm gonna switch gears now, Dale, and I'm dying to know personally, where is this technology going? Because in the linear mode, at some world, I should say, at some point we had manufacturers that were putting two linear lidar modes, looking in different ways. They're adding different frequencies, multi-frequency lidar, and in the forestry space, people used to get really excited about. Well, I shouldn't say used to. I think the jury's still out. How can multispectral lidar benefit the forestry space? Do you see that in the Geiger-mode going that direction in your plans, or is it still too early and you're still proving out the core technology? But I guess the question I want to ask is, the next 2 to 5 years out, where do you see Geiger-mode technology and your technology going? What gets you excited at night or the morning, I guess, of each day?
Yeah, for us as a company, the processing side, doing, speeding it up, getting it more efficient, and then more accurate. And to me, it's fascinating to think about the detection and the information theory side of it, of how much information can I really get from each photon? Because every photon is precious, and so how much can we learn from those? Intellectually, that's an interesting question, but more importantly, I think for in the forestry world, or frankly also in the urban mapping world, defense and security world, having algorithms that both run in close to real time, meaning it takes as long to collect the data as it takes to process the data. Being able to do real-time processing with high levels of detail and specificity and confidence, to me, that I think there's a lot of legs on that. The other thing is the feeding this data into sophisticated AI algorithms. Now, of course, you have to have training data to go along with that. So again, I think people who invest in that will be well rewarded, because computers are getting always faster, more capable, and all that sort of thing. So if we can take the digital signal processing, which is admittedly it's good, but it could there's still lots of approximations that are made, to be able to add more fidelity to the digital signal processing part of this, I think will be super exciting. Putting currently our system looks to one side of the aircraft. We can look up to 35 degrees off, but it's basically from vertical over to 35. So, putting two systems on, so we're looking both directions, certainly is a very straightforward step up. And then there's other ways that we can get more signal without using more laser power, which I'm excited about, which are in development.
Yeah, very, very, very cool. Yeah, even when you mentioned maybe putting two on, because you're already stitching scans together, that you just two x'd the number of scans one sensor might do. So yeah, definitely interesting from that point of view. Curious, in the Geiger mode space, obviously, 3DO is creating these systems. Are there a lot of you folks out there doing the Geiger stuff, or is it still pretty small niche? Because again, this sounds like, well, any lidar technology manufacturing is sophisticated, as evidenced by you coming out of MIT there on the physics side. It's not in every Joe can probably just buy, off Spark Fun online marketplaces and stitch together. But is this, what would you say? Like, I think I agree with you in the sense the forestry adoption, it's very early, being honest with you, exciting. But from a manufacturer side of things, is it still early for them, for you all too, or there's always been a large number of you that have done this and it's just the market wasn't ready to embrace this technology?
The community is pretty small. I'm not going to say I know everybody, but I probably heard of at least half of all people, individuals building Geiger mode lidar, with the exception of in the autonomous vehicle side. There was a big effort there. Unfortunately, there's been some changes there, and so there's kind of some revectoring going on there. But it is a small community, and I think, so our vision as a sensor manufacturer and giving people the tools to go do their projects as opposed to being a collector, I'm hoping that will lead to much broader adoption, and more transparency about how you actually process the data, because that's pretty critical. If someone's paying for data, they want to know what the recipe was that created that data.
For sure.
So this allows there to be more transparency in that process as well.
For sure. So I've got another really basic question. I was going to say dumb again, but I'm sure some people say it's like there's no dumb question. I'm like, oh no, I'm good at asking dumb questions, and I'm okay with that. Would I ever put one of your systems on a UAV, or and again, we know the payloads on a commercial UAV are pretty light, and I'm assuming your sensors probably exceeds maybe the lift of a UAV, but there's also bigger UAVs that can carry bigger payloads. But is that, I'm sensing that's probably not the space you're targeting. You're targeting more jet aircrafts that move. No, okay.
No, no. We're actively pitching ideas for, if you think about it like a 6-inch diameter pod, think about like a 6 inches by say 15 centimeters by 1.5 meters.
Thank you for the conversion to the Canadian here. Yeah.
I'm embarrassed. That kind of a pod, which happens to be the size of a Hellfire missile. It's entirely possible that with some, serious engineering, our system could fit into that kind of envelope. And then if you couple that with the real-time processing in GPU-based systems and some automated analysis, kind of first-order analysis to, help detect targets or that sort of thing, that feels to me like there's a good sized market that you can imagine where that might be useful.
Yeah.
And then, once you've done that on the DoD or the military side, there's absolutely uses for that, mounting that on a small Cessna or, those kind of single engine, single prop planes would be, if you can make these in volume, you bring down the cost, and therefore they're more accessible to people.
Yeah. So looking at my notes, there's one question I forgot to ask. And again, it's in the basic rudimentary category. I'll try and avoid using the D word. But LiDAR typically flies day or night, whether it's sensitive. So if we're working at the photon level, can we fly day or night? And is weather now more of a problem because it'll create more noise with the photon counting, or it don't matter?
The background light does give us more noise. And so, you saw how we have ways to go through the point clouds and try to figure out where there's concentrations of signal. So that gets stressed a little bit more. And to be able to overcome the noise, maybe instead of planning for an average of 10 detected photons, maybe we increase it to 15. It's not a showstopper. It does reduce the efficiency slightly, but it's definitely not a showstopper. And in fact, being able to fly day or night as compared to, passive systems means you have twice as many hours of the day in which you can avoid weather, So obviously if there's fog or, clouds or things like that, we can't see through that. It's normal optics that any lidar system has to deal with.
Sure. Cool. So looking forward, I've taken your thinking or stretched you 2 to 5 year out. You're a technology guy, so technology, like, we're working at a certain period of time, but I suspect, again, you're commercializing technology, you're an entrepreneur, the brain probably don't shut down at 5 p.m. on a weekday, and your family's probably like, he keeps talking, he's always working, but that's the benefit or maybe the curse of being an entrepreneur. But what does 10 years out look for you? Do you see a different version of Geiger or something else coming? Like, because again, we got linear mode, Geiger, single photon. Is there something else that excites you, or do you think we've kind of pushed the limits of lidar technology, and now it's really about fully commercializing, building pipelines to provide almost real-time data processing? Where do you see that 10-year world look for 3DO and yourself?
Yeah, well, I think making better engineered systems that are super reliable, that are compact. And I look at some of our competitors on the linear mode side, and they have some really nice systems. They're very well built. They're easy to use. You turn them on and they work. Or at least that's my impression. I assume that's the case. And we would like to do that. So that's not 10 years. That's more like three years to do that sort of thing. But then, one of the promises of Geiger mode technology is you need 1/10 or 1/20th of the amount of light. So you should be able to make these systems more capable and smaller and cheaper than things that require, a lot more light. So making these things small and compact, like I mentioned, the 15 centimeter by 1.5 meter. That would be for higher altitude, but for lower altitude things, you could make it even smaller. So those kind of things get us excited. And then I think the processing side, which is really kind of half of the system in the sense that you get your raw detections, but you got to make sense of them. I think there's a lot of exciting growth to be had there. And, working with CUDA cores to do processing is really attractive and very beneficial. So it's the same stuff that a lot of other people talk about, but I think it is kind of cool. But what it enables, really, that I do get excited about the application side is, repeat mapping of, important forest resources. For example, is there illegal logging going on? Let's go map large sections of Costa Rica, or, pick your country where there's heritage, or there's really valuable trees that loggers, illegal loggers like to go in and cut down. Obviously, you can see from the data I showed, you can look in the forest and say, hey, that tree's missing. And you can have an algorithm that does automated change detection to say, a year ago, there was a tree there. We gave those guys a permit to do something in here, but it wasn't to cut that tree. So in enforcement, then there's also, people continue to use lidar for archaeology, and we would absolutely like to get into that support role to support the archaeologists in what they're doing. Documenting carbon capture and sequestration in forests is really important. And then there's at a city scale, that's not the forestry side, but on other markets, helping urban planners, the smart city initiatives, all the digital twin stuff. I think we have a really important role to play there, because we can get, those high resolutions, 10 centimeters at large scales very rapidly. So anyway, excited about that. we'll see
Yeah.
how it all goes. There's a lot of shaking out to do in the different technologies. And I think, frankly, there's a really important place for the different kinds of technologies.
Yeah, no, I get excited just listening to you, and I can sense the passion, at the start. But when you go to Costa Rica, call me. I'm happy to sit on the base station with my Mai Tai, my flip flops, my beach chair, and maybe sunscreen on my nose, and just give me a call. Happy to back you up on that
All right, sounds good.
project there. So as we look to wind down, I know one of the things you provided me in prep was there's a presentation that you did. I can't remember the conference or event, but for our listeners and viewers, if you're interested in seeing more visuals and how the technology works, I thought it was a great presentation.
Thank you.
Tell me more about that. Was it
This was a Optica conference. It was over in Barcelona last December, which was a nice trip.
You didn't call me for the Barcelona trip, Dale? Come on.
Come on. Yeah. So so there's the presentation I gave there as part of a seminar. Great conference, meet a bunch of people and share some ideas. So yeah, I'd be happy to share that. And we are also developing a series of small, short explainer videos, which we have to get up on the right host at the right time, but definitely working to make those just to kind of help people understand kind of some of what we've talked about here, make it into small chunks.
For sure. Well, I suspect some of our viewers and listeners around the world, their interest has been piqued. For those who want to get a hold of you to follow up, what's the best ways? The website, social, LinkedIn, email? What do you suggest? What's the best way to reach out to you?
I would send an email to sales at 3deolidar.com, or just to me personally, it would be fine too. Dale Fried, DALEFRIED at 3deolidar.com.
There you go. Perfect. Excellent. So for everyone in the digital forester community, encourage you to reach out if you want to learn more about this Geiger-mode technology, lidar technology. It's super cool. That's all I can say. I was blown away by some of the images we've seen. So Dale, thanks so much for joining. I hope you enjoyed the conversation. I learned tons, and I'm sure our community is also going to thank you for explaining how this technology works and how they could potentially benefit. So thanks so much for your time. I look forward to seeing you maybe in person at some point in the not so far future.
Yeah, absolutely. And thank you, Kevin. And I look forward to learning more from your listeners as well. Please contact me. Happy to talk and listen, more importantly, about what you're trying to accomplish.
For sure. Awesome. We'll talk soon.
Take care.
Okay. Bye-bye.